In this video, we're going to study orthogonal projections. I don't feel like your book does a very good job of explaining what an orthogonal projection is, so I'm hoping I'll do a better job than your textbook. Essentially, an orthogonal projection is a decomposition of a vector into the sum of two orthogonal vectors. So in my picture here, I'm saying I want to be able to write vector y, this guy right here. I want to write that as the sum of two vectors that are orthogonal. And so this is called a projection because if you can try to imagine this vector v, my little pink vector, and I know that that line L is essentially created by all of the scalar multiples of vector v. So C is some real number, and I'm basically taking v times all of these scalars, and that creates this line. The projection of y is if I were to imagine some light that is perpendicular to line L, and I'm looking at the shadow that y would create, that's essentially what I'm doing, is I'm looking to write y as a sum of some scalar multiple of v and then that distance from y to v that is orthogonal or that is a right angle. So we have some different notation here, and really there's only one formula, and that is how to determine y hat, which is the projection of y onto L. And again, that has to do with dot products. So I'm going to take y times the vector, the dot product of y and the vector over the dot product of the vector and itself multiplied by the vector. So this is not going to make any sense until we actually do a question, but before we started process of actually finding an orthogonal projection, I wanted you to get an idea of what we're doing. So again, we have this vector y. We want to write it as the sum of two orthogonal vectors, so two vectors that are at a right angle to one another. And so that would be some scalar multiple of v plus some vector that is orthogonal to v. So let's take a look at how we'll actually go about doing this. We're going to do this practice question together step by step. And again, I tried to write it out exactly what we would do or the process that we would do. So what we're looking for, the first thing is we have two vectors and I want to find the orthogonal projection of y onto u. So again, if you think about that last slide, u would be that vector, v was the vector on my last slide. So I'm looking at that line that would be created by u and say what would that projection of y look like if there were some ray of light shining perpendicularly to u, what would y look like projected onto that line? And again, this one's easy to determine because we are just looking at a formula. So y hat, which is a projection, is found by taking the inner product of y and u, so that's 7 times 2 or 14 plus 6 times 1 or 6 over the inner product of u with itself. So that's 2 times 2, which is 4, and 1 times 1, which is 1. And that's going to be taken times vector u, which means I have 20 over 5 times vector u, which means 20 over 5 is 4 times vector u. So my projection is 8, 4. So again, if you were to graph that, you would be looking at 7, 6, and the line created by all of the scalar multiples of u along the line created by 2, 1, which obviously 8, 4 is on that line. And that is where y would sort of land if we were looking at the projection of y onto that line. Step 2 then is to find the component, which is what I would add to the vector that I just found in my last question, or last part of the question, so that I can write y as the sum of two orthogonal vectors. So one is in span u, well that's the one we just found. So if you'll recall, I just found that y hat was 8, 4, and if I had a coordinate plane here, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 8, 4 is out here, and u was 2, 1. So it's pretty easy to see, and I don't have a ruler handy, but we can see that that line L, what I was looking for was the one vector that was on the line. That's the one that's in the span of u, and certainly 8, 4 is in the span of u. And then I want to find one orthogonal to u, so at a right angle or perpendicular to u, that would allow me to arrive at 7, 6. So 7, 6 is about right here. So let's take a look. All I have to do is use this formula that says 7, 6 minus 8, 4, so y minus y hat. 7 minus 8 is negative 1, 6 minus 4 is 2, so negative 1, 2. Now if I think about the parallelogram rule, this makes perfect sense. So what I have found is the projection of 7, 6, so 7, 6 is this guy. I have found that as the projection and the component that are orthogonal to one another. So the question asks me to write y as the sum of two orthogonal vectors, so that sum would simply be 8, 4, which is the one that's in span of u, and then the one orthogonal to u is negative 1, 2. And obviously I can check this by saying 8 plus negative 1 is 7, 4 plus 2 is 6, and that does get me back to y. The last part, which is completely optional, but if you want to check your work and you want to make sure that you did everything right, the last step is to verify that the set of vectors that we just came up with is in fact an orthogonal set. And that's the easiest part. So we have already done all of the hard work to find the projection, which is 8, 4. And then we already found that y minus y hat is negative 1, 2. And we know how to see whether or not something is orthogonal. We're just going to find the dot product. So I'm going to take the inner product of y hat, and then of course the difference, y minus y hat, which means I'm going to take 8 times negative 1 plus 4 times 2, which is negative 8 plus 8, which is 0. And there I have verified that because the inner product of the two vectors is 0, that the set of vectors is an orthogonal set. And again, I'm saying it in words. You, as a student, would write that down on your paper, because you wouldn't just find 0 and say, yes, it's orthogonal. You would explain why finding that 0 tells us that the set is orthogonal.